Okay, in this lecture, we're going to talk about how to write chemical reactions and use them for calculations. So if I want to make a bike, I know I need wheels and a frame. And in particular, I need 2 wheels and 1 frame to make 1 bicycle. Well, I can write that as an equation. I can say 2 wheels plus 1 frame yields 1 bicycle, where the wheels and the frame are my reactants and my product is the bicycle. You can do the same thing for chemical reactions. If carbon and oxygen react together, they make carbon dioxide. So I can write this as carbon plus oxygen yields carbon dioxide. Here are symbols that we use when we write chemical equations. A plus sign separates 2 or more formulas. The arrow means we react to form products. Excuse me. S means we have a solid, L means liquid, G is a gas, AQ is aqueous, which means dissolved in water, and then an arrow with a delta above it means the reactants are heated. It's really important to include the states of matter, this S, L, G, or AQ, in your chemical reactions if you know them. So once we write a chemical reaction, we have to balance it because we can't the reactant atoms must equal the product atoms. We can't create or destroy matter. So if I have this reaction, this is saying I have solid iron 3 sulfide reacting with hydrochloric acid to make aqueous iron 3 chloride and hydrogen sulfide gas. If I do a count of my different elements in my reactants and products, I can see they're not equal. I have 2 irons in my reactants but 1 in my products, 3 sulfurs in my reactants but 1 in my products, 1 hydrogen in my reactants but 2 in my products, and 1 chlorine in my reactants but 3 in my products. So you have to put numbers in front called molar coefficients to make it so the reactants and the products equal each other. So here's the balanced chemical equation. So what I did is I first looked at the number of irons. I said I have 2 here but 1 here. So I put a 2 in front of the iron 3 chloride to show that now I have 2 irons and now my irons are equal. Then I looked at the chlorines and I had 6 here because I just put the 2 in front, and how I got that is I took the coefficient and I multiplied it by the subscript. So 2 times 3 is 6. So I put a 6 in front of hydrochloric acid. Now I have 6 chlorines. Then I looked at my sulfurs. I have 3 sulfurs here, but I only had 1 here, so I put a 3 in front of my hydrogen sulfide gas. And then I checked my hydrogens. I have 6 hydrogens here, I have 6 here, 3 times 2, and so I'm good to go. So it's just an accounting thing. You just keep track of the elements on the left, elements on the right, and make sure they equal each other. And you just put numbers in front of the different molecules, the different reactants or products, in order to make them equal on each side. If your reaction has a polyatomic ion in it, you balance the polyatomic ion as a group. So here I have sulfate ions in sulfuric acid and aluminum sulfate. So I don't balance each sulfur individually on each side and each oxygen individually on each side. I balance the sulfate ions as a whole. So if I'm counting, doing my initial accounting, I have 1 aluminum in my reactants, 2 in my products. I have 2 hydrogens in my reactants, 2 in my products. I have 1 sulfate ion in my reactants, but I have 3 in my products. So the first thing I want to do is I want to balance my sulfate ions. So I need to put a 3 in front of my sulfuric acid. Now I have 3 sulfate ions here and 3 here. Then I want to balance my hydrogens. So because I put a 3 here, now I have 6 hydrogens, 3 times 2. So I put a 3 in front of hydrogen gas. And then I look at my aluminums. I have 2 aluminums here, so I put a 2 in front of the aluminum here, and now I'm equal. So just a tip is that it's easiest to balance, to save things that are by themselves. So like here's hydrogen by itself, here's aluminum by itself. Save those for the end because it's really easy to balance those. So you should first balance things that are bonded to other things in both the reactants and products. So here's some practice problems, and here are the answers. So I suggest you go through these by yourself. So you'll have to go from the words to write the reaction and then balance it. But this is a good test on not just balancing chemical equations, but also nomenclature, being able to go from the names to the molecule. Okay, So I can actually use the balanced chemical equation to do calculations. And you can use the molar coefficients to determine molar ratios between reactants and products. And these are the molar coefficients, the numbers that we changed in order to balance the reaction. So what this is actually saying is that 2 moles of iron reacts with 3 moles of sulfur to form 1 mole of iron 3 sulfide. The numbers in front, you can just use them as mole ratios to do calculations. So you can compare how much iron reacts with how much sulfur by using these molar coefficients, or how much iron will make how much iron 3 sulfide, so on and so forth. So let's look at an example. So how many moles of sulfur are needed to react with 1.43 moles of iron? How many moles of iron 3 sulfide are formed? Okay, so what I do is I start with what I know. So if I have 1.43 moles of iron, my conversion factor are my molar coefficients from the balanced chemical equation. So I want to get rid of on the bottom, which is moles of iron, and I want moles of sulfur, so that goes on top. And I say 2 moles of iron for every 3 moles of sulfur, and those are just the coefficients from the chemical reaction. And I get 2.15 moles of sulfur. That's how many moles of sulfur I need to react with this many moles of iron. Then I want to know how many moles of iron 3 sulfide are formed. Oh, and yes, so my units cancel. Okay, so how many moles of iron 3 sulfide are formed? Same idea. I start with what I know, 1.43 moles of iron. I put moles of iron bottom, because that's what I want to get rid of, and then I put moles of iron 3 sulfide on top, that's what I want to get. And I know that for every 2 moles of iron, there's 1 mole of iron 3 sulfide. I get that from the balanced chemical equation. My units cancel, and I get 0.715 moles of iron 3 sulfide. So again, you just use these as conversion factors. And you can compare reactants to reactants and reactants to products, products to products, this way. So here's some more practice problems. So if we have 2H2 plus O2 yields 2H2O. So how many moles of oxygen are required to react with 2.6 moles of hydrogen? Well, for my reaction, I know my balanced chemical equation, I know that for every 2 moles of hydrogen, there's 1 mole of oxygen. So I start with what I know, 2.6 moles of hydrogen. Then I multiply it by 1 mole of oxygen over 2 moles of hydrogen. And I get 1.3 moles of oxygen. Again, this 1 and this 2, they just come from my molar coefficients from my balanced chemical equation. How many moles of hydrogen are needed to react with 5 moles of oxygen? Well, I use my same ratio. I start with what I know, 5 moles of oxygen. And I multiply that by 2 moles of hydrogen over 1 mole of oxygen. Again, I get those numbers from the balanced chemical equation. And I get 10 moles of hydrogen. So that means if I have 5 moles of oxygen, I need 10 moles of hydrogen to react. Finally, how many moles of water form when 2.5 moles of oxygen reacts? Okay, well, we need a new ratio now. So for my chemical equation, I know for every 1 mole of oxygen, 2 moles of water is formed. So I just do the same thing. I start with what I know, 2.5 moles of oxygen. I multiply it by 2 moles of water over 1 mole of oxygen. I get 5 moles of water. So for every 2.5 moles of oxygen that reacts, I make 5 moles of hydrogen. Again, these conversion factors just come from my balanced chemical equation. We can do the same thing with mass. So we can, if we're given the mass of a reactant or a product, we can figure out a mass of another reactant or product. We just have to go through moles. Remember, you always have to go through moles. So the first thing you'll always do is go convert to moles, and then you can compare moles of one thing to moles of another thing, and then you can go back to grams. So here's a chemical reaction here. So this is acetylene plus oxygen gas yields carbon dioxide and water. So how many grams of carbon dioxide are produced when 54.6 grams of acetylene are burned? Okay, well, I start with what I know, which is 54.6 grams of acetylene. I need to get that to moles. So remember, in order to do that, I use the molar mass, which I calculate. And the molar mass is 26.04 grams per 1 mole. Put grams on bottom because that's what I want to get to, and I want to get to moles, so that goes on top. Okay, grams cancel. Now I want to go from moles of acetylene to moles of carbon dioxide. How do I do that? I just look at the molar coefficients. So I want to get rid of moles of acetylene, so I put that on bottom, to go to moles of carbon dioxide, so I put that on top. I know that for every 2 moles of acetylene reacting, I make 4 moles of CO2. Again, I get that from the balanced chemical equation. So now I'm in moles of carbon dioxide, but I want the mass of carbon dioxide. So to get from moles of carbon dioxide to grams of carbon dioxide, I just use the molar mass. So I know that for the molar mass is 44.01 grams per 1 mole. Units cancel. I'm left with 185 grams of carbon dioxide. So if you're given a problem like this, all you need to do is you start with the mass you're given, you convert that mass to moles, you use the molar ratio from the balanced chemical equation to convert from moles of one thing to moles of the other thing, and then you use the molar mass to convert to grams. Here are some practice problems. Here's another practice problem. I suggest you try this on your own. So the reaction is sodium metal plus oxygen gas yields sodium oxide. And so here are 3 different problems that you should try with this. And I really suggest you do lots of practice problems for these different calculations. There's tons in your book. Just because if you do a lot of these problems, they're very repetitive and you'll get really good and really fast at doing them. So I suggest you do lots and lots of practice, and then it will just become like second nature to do problems like this. Okay, last thing we want to talk about are limiting reactants. So oftentimes when we do a chemical reaction in a lab, we have less of one reactant than another. So the limiting reactant is the reactant that makes the least amount of product. It's not necessarily the reactant we have in the lowest amount. It's the reactant that will make the least amount of product. That's a distinction you need to make. The theoretical yield for a reaction is the amount of product that can be made in a chemical reaction based on the amount of limiting reactant. So that's saying if I look at my limiting reactant and I have X number of moles, my theoretical yield is how many moles of a product I should make from that number of moles of reactant. The actual yield, though, for a reaction is the amount of product that's actually made when you run a reaction. And then the percent yield is the percentage of the theoretical yield actually made. So pretty much never do you actually make the theoretical yield when you run a reaction in the lab. So then this is due to a lot of things. Reactions don't always go to completion, or they take a long time to go to completion. You can lose product by different methods, drying methods or purification methods. There's lots of different ways that you can lose a product, or you spill a little bit when you're going to weigh it. Lots of different things. So very rarely would your actual yield be the same as your theoretical yield, but it's good to know how much you should make. And then you can compare how much you actually make to how much you should make. If you made more than you should have, something went wrong. Either your product's not pure, so you have something else mixed in there. Your product might be wet and might have water on it or another solvent. There's lots of different things. So the theoretical yield is really, really helpful in a real-world lab setting because we compare our actual yield to the theoretical yield. If I make more than the theoretical yield, that tells me something about the product or what the reaction that I did. If I make less, that tells me something else. Generally speaking, it's better story if you make less than if you make more. But it's a very, very important thing for a lab. But again, if you're ever in a lab or you're doing labs, at home, if your actual yield doesn't equal your theoretical yield, don't panic. It'd be much more alarming. I mean, not necessarily alarming, but it would raise a flag if they did actually equal each other. So that's just something to keep in mind. I think a lot of students get hung up on that. And it's not that we're trying to make sure, we actually made every single mole we should have made. It's not that. It's the comparison tells us something about the reaction and what happened. So let's do some practice. So consider this reaction. I have solid aluminum, reacting with chlorine gas to make aluminum chloride, solid aluminum chloride. So if I have 0.552 moles of aluminum and 0.887 moles of chlorine, what is the limiting reactant and the theoretical yield of aluminum chloride? Again, I can't say that the limiting reactant is aluminum because I have less moles of it. It might be aluminum, but it also might be chlorine. Because remember, the limiting reactant isn't the reactant that's present in the smallest amount. It's the reactant that will make the smallest amount of product. So when you have a problem like this, you need to calculate how many moles or how many grams of product I'll make from the given quantities of the different reactants. So that's what we'll do. So first, we'll look at how many moles of aluminum chloride I can make from 0.552 moles of aluminum. So we just did this before, right? So I start with what I know, which is 0.552 moles of aluminum, and I multiply it by the molar ratio of aluminum chloride to aluminum. I get that from my reaction. I know for every 2 moles of aluminum, from the 2 here, I'll make 2 moles of aluminum chloride. That's how I got this. So I'll make 0.552 moles of aluminum chloride. Then I look at the other, this should say chlorine, not aluminum. If I have 0.887 moles of chlorine, how many moles of aluminum chloride will I make? Okay, well, I multiply that by the molar ratio of aluminum chloride to chlorine gas. Again, I get that from the chemical reaction. I know that for every 3 moles of chlorine gas, I'll make 2 moles of aluminum chloride. So if I have 0.887 moles of aluminum, of chlorine, I'll make 0.591 moles of aluminum chloride. So that means this is my limiting reactant. So it just so happens that my reactant present in the lowest amount is my limiting reactant, but again, it's not always the way it is. If that's how it is, it's just coincidence. So again, aluminum, my limiting reactant, because I'll make less aluminum chloride from this amount of aluminum than this amount of chlorine. And then this is also my theoretical yield of aluminum chloride. So your theoretical yield is equal to the amount of product that you'll make from that specific amount of your limiting reactant. So now, say I ran this reaction in lab using the amounts of reagents given on the previous slide, and you found you made 0.458 moles of aluminum chloride. What's the percent yield? So the equation for percent yield is equal to actual yield over theoretical yield times 100. So my actual yield is 0.458 moles. That's how much I made in the lab. But I should have made 0.552 moles. That's what we calculated on the previous slide. So I divide those and multiply by 100. I get 87.9% yield. This is a pretty good percent yield. So we can do the same thing if we're given masses, not moles, just like a couple slides ago we did. So let's look at this reaction. So here we have copper 1 oxide reacting with carbon to make copper metal and carbon monoxide. Okay, so when 11.5 grams of carbon reacts with 114.5 grams of copper 1 oxide, 87.4 grams of copper metal are obtained. So first we need to determine the limiting reactant, then we need to determine the theoretical yield, and then finally we'll determine our percent yield. This here is my actual yield. I did this reaction, I had 11.5 grams of carbon and 114.5 grams of copper 1 oxide, and I found that I made this much copper metal. So determine the limiting reactant is the same thing we did before. We'll look at our 2 reactants, those amounts, and we'll figure out how much copper I can make from those amounts. So first let's look at carbon. So if I have 11.5 grams of carbon, the first thing I need to do is go to moles of carbon. Always go to moles first. I use the molar mass to do that. So I put grams of carbon on the bottom, moles of carbon on top, because I want to get rid of grams and I want to go to moles. Now that I'm at moles of carbon, I can compare moles of carbon to moles of copper by using the balanced chemical equation. I know for every 1 mole of carbon, to get here, I make 2 moles of copper. Now I'm in moles of copper. But I want the mass of copper. So I just use the molar mass of copper to go to grams of copper. So it says if I have 11.5 grams of carbon, I should make 122 grams of copper. Now let's look at copper monoxide. So if I started with 114.5 grams of copper monoxide, I'm sorry. I need to get to moles of copper monoxide. I do that using the molar mass. Then I want to go to moles of copper. I do that using the molar ratios from the chemical equation. For every 2 moles of copper, to make 2 moles of copper, I need 1 mole of copper monoxide. So now I'm in moles of copper, but I want the mass of copper made. So I use the molar mass of that. So this says that for 114.5 grams of copper monoxide, I should make 101.7 grams of copper. So this is my limiting reactant, copper monoxide, and my theoretical yield is 101.7 grams of copper. So you can see here, I have way less carbon than copper monoxide by mass, but that was still my limiting reactant. So now I know my theoretical yield is 101.7 grams of copper. I know my actual yield was 87.4, so I can determine my theoretical yield. Again, we use this equation. I do take my actual yield, I divide it by my theoretical times 100, and I get 85.9% yield. Pretty good percent yield. So again, I really encourage you to do lots of practice problems because there's just a lot of math. It's not new math, but there's a lot of math in this chapter. And if you do lots and lots of practice problems, again, you'll become really comfortable with it and you'll be able to do these problems really quickly. But we'll be doing problems like this throughout the rest of the semester.